Hello students, so welcome to this lecture on optimizing the sizes for a single path digital circuit. So in a digital circuit we might have multiple paths, that is something we will see later. We will analyze those circuits and then components of the size of those circuits later on. But to begin with, I think we will do a single path digital circuit and then try to optimize the sizes of those gates as well as the transistors to obtain a minimum delay. So this lecture will talk about how do we go about optimizing the sizes. Right, so let's proceed or begin further. Okay, so this is an empty slide, so I need to draw a gate size of 2:1 inverter. So let me pick up my pointer. So let's say that I have an inverter. So I have a PMOS and then an NMOS circuit. So I'm going to draw those VDD and then the ground rail, and then I have a bubbled gate which represents the PMOS circuit. So if suppose this is the size of a 2:1 inverter, which is generally our benchmark inverter. So what it means is at the input side, I will have a capacitance of 3C. So this particular inverter, which is of 2:1, is actually represented in the form of the size of 3, right? So the gate size is 3 here. So I'm going to write it as a gate size representation says that it's an inverter, and then the size is 3, and then this is the transistor level sizing, which is 2:1. Right, so this is how we will represent a gate size from the transistor. So if suppose I have an inverter, so let me pick up another pointer. Let me say that I have an inverter here and its gate size is 6. Right, so what it represents is on the transistor level. So let me draw the transistor level, PMOS and NMOS. That is the VDD and then the ground rail. And then this is the PMOS transistor and then the NMOS transistor. So it sees a capacitance of 6C at the input side. And we know that, in a long channel current model, we need twice the size of the PMOS transistor as that of the NMOS, so that, to leverage the beta values to be same, so that I'll get the same current, rising current and then the falling current, which will give me the falling resistance and the rising resistance to be same. So in that sense, what we want is from this 6 size or whatever, the 6C capacitance, so we need to accommodate 2 by 3 parts multiplied by 6. So that will be the size of 4, which will go to the PMOS side, and then the size of 2 will go to the NMOS side. What it means is I will do 1 by 3 parts of this 6 value, and then 1 by 3 parts of that 6 value will go towards the NMOS side, and then 2 by 3 parts of that 6 value will go towards the PMOS side. And that's how I represent the size of 4:2, right? So if, in case I have a different size, so let me take up an inverter, let's say it has a size of 10. What it means is I will need 2 by 3 parts of 10 on the PMOS side. So this will go to the PMOS side. So the size, the PMOS transistor width will be 2 by 3 multiplied by 10. And NMOS will have 1 by 3 parts of 10. So which will be nothing but 6.66 and 3.33 respectively for PMOS and NMOS. Right? Hope this is clear. And this particular notation of the gate size, and then from the gate size allocating the necessary or the required widths to the PMOS and NMOS transistor is what we are going to follow from here on. Right? So moving further. So let's say that if I have a size of 10 here, so that's what I had put it previously. So size of 10 here. So 2 by 3 parts will go to the PMOS side, and then so this is 2 by 3 parts. And then the 1 by 3 parts will go to the NMOS side, because I want 2:1 ratio, so that in a long channel model I'll get the same current, the rising current as well as the falling current. So that's the reason why we want the two parts, double the parts to be going towards the PMOS side, and then single parts to be going towards the NMOS side. For a two input NAND gate, so two input NAND gate, right? So if I draw the two input NAND gate, so let me draw here because I have a space here. So so this is the series on the pull down side, and then I will have it two transistors which are in parallel on the PMOS side. So this will be my VDD, and then the other rail will be ground. PMOS transistor, I'll just represent it in a bubbled transistor form. I'll use a different pointer so as to put the width. So what we have seen is we have used 2:2 here, 2:2 here. This 2 will give me a, the falling resistance of R matches with that of the 2:1 inverter's falling resistance. And under worst case condition, either of these transistors will be on, and thereby will give me the rising resistance of R, which matches with that of the 2:1 inverter's rising resistance. So here, the input side, so if I pick up, this being my transistor A, or the input A, which goes to this particular transistor and then this particular transistor. So if I see that, so the size of the of the two input NAND gate here, the input size of the two input NAND gate is nothing but 4. Right, where 2 parts are going to the PMOS, and then 2 parts are allocated to the NMOS, right, equal parts. So if I have a size of Y here, right, so total should be Y here. That means that out of 4 parts, 2 parts of the Y will go to the PMOS one, and then out of the 4 parts, 2 parts will go to the NMOS one, right? So that's the reason why we have done the 4 parts, and then 2 parts will be going towards the NMOS, and then 2 parts will be going towards the PMOS. So if I create 4 parts, Y by 4 multiplied by 2 turns out to be Y by 2. And that's what we have it here, Y by 2 here, and then the Y by 2 here. So it's basically creating 4 parts, and then 2 parts allocated to PMOS and NMOS respectively. And again, we are at this point of time, we are assuming symmetric gates. So let me write it down, symmetric gates. What it means is both the input sees the same gate size. Both the input sees the same capacitance, input capacitance. Right? We will, later on in the future slides, we will see the asymmetric gates. But at this point of time, we are assuming that the gates are all symmetric. So all the input sees a same capacitance. Right? Hope this is clear for a 2-input NAND gate. Moving further, 2-input NOR gate. 2-input NOR gate again. So we will have, let me draw the 2-input. This is 2-input NOR gate. So let me draw it. So 2 of the transistors on the pull up side to be in series, and then 2 of them will be in parallel on the pull down side. So this is my VDD. And this is my ground, and this is my PMOS, this is my PMOS, this is this. Let me put up the size here. I need a size of 4 here on the 2-input NOR gate side, and a size of 1 here, so that the equivalent rising resistance is R, matches with that of the 2:1 inverter. And then on the worst case condition, 2 of the parallel NMOS transistors will give me a falling resistance of R. Right. So what we will do is, for each of these inputs, so if I connect these 2 inputs together, so this will be the first input A, and the other one will be the B. So the gate size, so the put together, it will be phi, right? So this will be represented as a NOR gate of size phi, right? Where 4 parts are going to the PMOS, and then 1 part is allocated to the NMOS. So given an X size here, so we will create 5 parts, and then 4 parts will be going to the PMOS side, and the remaining 1 part, so X by phi multiplied by 1 will be going towards the NMOS side. So that's what we have, X by phi here, and then 4 by phi X. And again, it's a symmetrical gate. So both the inputs should see the same capacitance of X. So 4 by phi X will be given to the other input PMOS transistor, and then X by phi will be given to the other inputs NMOS transistor. So put together, the overall capacitance seen at the input side will be X. Again, hope this is clear. Moving forward, so let's take this particular single path example. So I have now 4 gates. This is my input. So let me say that the input is here, and this is my output. So I'm going to represent it as Y, right? And then I have 4 gates. The first one is the inverter, the second one is a 2-input NOR gate, third one is the 2-input NAND gate, and then the fourth one is the inverter again, which is connected to a load capacitance of 20, right? 20 into C, where C represents 1C unit NMOS capacitance, right? So if I choose a unit NMOS transistor, the width will be 100 nanometers. So whatever its parasitic capacitance, that will be the 1C, right? That, if we know the unit transistor, its capacitance should be nothing but close to 1.1 femtofarads. Right, so we have converted this load capacitance into 20 multiplied by the unit NMOS transistor capacitance. So whatever is the capacitance, if it is actually 2 femtofarads, we are going to represent it as 20 into C, where C represents the unit NMOS transistor's capacitance, which is nothing but 0.1 femtofarads. Right, hope this is clear. And then we have allocated the size of X, Y, and Z in this particular gates. And at the input side, the inverter has a overall gate size as 10. That means in this particular input, it sees a capacitance of 10 into C, where C represents nothing but the same unit NMOS transistor capacitance. All right. So no, that's why we have written down everything in the form of a unit NMOS transistor. So because when we find out what is X, Y, and Z, we can easily relate it to what should be the transistor's capacitance. All right. So what we are going to do now is we are going to write an expression for the delay. And what we ultimately want to do is find out this X value, find out this Y value, and find out this Z value, so that my overall delay for this particular circuit will be minimum, right? So the intention of this particular of this particular task is to find an optimum value of X, Y, and Z such that my overall delay will be very, very less, should be minimum, right, for this particular path from input to output. So we are going to use a linear delay model. So we are going to use a linear delay method or a model. So I need individual stages, whereas the individual stages I have written it as 1 stage, 2nd stage, 3rd stage, and 4th stage. Individual stages, the logical effort, which is nothing but G, and then the parasitic, normalized parasitic P, and then the H value, which is the electrical effort or the fan out H. And then what we can do is we can do a summation of all the 4 stages from 1 to 4, right? And then Pi plus Gi Hi, which will give me the overall delay. Okay, so that's why I've written this G value. So individual stages D, P, and H values, individual stages D, P, and H values, individual stages D, P, and H values. Now let's try to understand what is this G value and P value and H value. Is it correct? So for an inverter, the logical effort is nothing but 1. So I have written it as 1. For a 2-input NOR gate, the logical effort is 5 by 3. For a 2-input NAND gate, the logical effort is 4 by 3. And for an inverter, again, it is nothing but 1. Right? So this particular portion is, that is something we have taken it, or we had seen that earlier. So this is done. The normalized parasitic, for the NOR and the NAND gate is equal to the number of inputs. Right, so if it is 2-input NOR gate, we will have the normalized parasitic as 2. If we have a 2-input NAND gate, the normalized parasitic is 2. Inverter, the parasitic, normalized parasitic value is nothing but 1. Finally, the electrical effort for the individual stages. The electrical effort, as per the definition, it is nothing but the input capacitance divided by whatever it sees, the input capacitance here on this particular first stage. If I consider, it is nothing but the input capacitance which is loaded, the input capacitance of the second stage which is loaded into the first stage. So that will be nothing but X into C divided by its own input capacitance, which will be 10 into C. So it will be X by 10. Similarly, the H value for the second stage will be nothing but the input capacitance of the third stage, which is loaded into the second stage. So it will be YC divided by XC. So Y by X. And for the third stage, it will be ZC divided by YC. So it will be Z by Y. And then the last stage, the fourth stage, it will be 20 by Z. Right. So hope, the G, P, and H of the 4 stages are individually validated and verified. So what should be the overall delay for this 4 stages? It will be nothing but the individual stages, P plus GH, and then the summation of all the 4 stages will give me the overall delay. And that's what I have written here, P1 plus G1H1 plus P2 plus G2H2 plus P3 plus G3H3 plus P4 plus G4H4. Right, so this will give me a delay value. If I know the value of X, Y, and Z, I should be able to find out the overall delay for this particular 4 stages. Although it will be a normalized delay, but that is perfectly fine, because once I get the normalized delay, multiplied by 3 into RC will give me the absolute delay of any critical path. Right, hope this is clear. Moving forward, so I have this particular critical path circuit, and then the delay of this is written here. So this is the parasitic of the first stage, and then the G value is nothing but 1 multiplied by H value is X by 10. Right, so it will be X by 10 value. Plus the P value is nothing but 2 here, plus G will be 5 by 3 into Y by X. And then this will be nothing but 2 for the third stage. It will be 2. This is the second stage, and then this is the first stage. So it will be 2 plus G will be nothing but 4 by 3 multiplied by Z by Y plus 1 plus, so this will be 1 plus 20 by Z. So that's what we have. So here it is X by 10. So overall what we get is, so this is X by 10. Yeah, so overall delay is nothing but 1 plus 2 plus 2 plus 1, which is 6 here, and then the rest of this X, Y by X, Z by Y, and then 20 by Z. So this is what we get. Right, so this is the overall delay. Now notice this X value and Y by X and then Z by Y and 20 by Z, right? So what I'm going to do is, so this is kind of an empty slide. So I have some space here to write it down. So I'm going to concentrate on the 2 aspects. So delay, what we had got was 6 value, the summation of all the parasitics, plus the summation of all the the GI, HI. I can write it down. So it turns out to be nothing but 6 plus. So if I write it down, it will be nothing but X by 10 plus 5 by 3 Y by X. So this is my Y plus 4 by 3 Z by Y, and let's say this is connected to, we said it is connected to 20C. So it will be, G will be 1 and then 20 by Z. Okay. Okay. So if I concentrate on this particular portion, what it says is, say this 6 is a constant, so we cannot vary this because 6 is already a value that has been given. So if I somehow vary this X value, let's say if I increase this X value, so I will have an increased value here, but I will have a overall Y by X value is going to decrease. So overall Y by X into 5 by 3 is going to decrease. Right? So we don't know what values of X we will get an optimized summation results. Right? If I increase an X, or should I decrease an X, so that if I decrease the X, this quantity will decrease, this particular quantity will decrease, but this quantity will increase. And similarly, if I increase the Y here, right, let me use a different color. So if I increase the Y here, there will be this particular component will decrease. However, this particular 5 by 3 Y by X is going to increase. Right? And similarly, if I decrease or increase the Z value, this particular component will also be changing. Right? So there lies an optimum value of X, Y, and Z such that we should be able to get a minimum value of this summation, of this particular summation. All right. So that's what we need to find out. So let's say, so I'm going back to this particular slide. So let's say that I have this particular value as A. I have this 5 by 3 into y by x as B. So this is my B value. And 4 by 3 z by y as C. And 20 by z as D value. Right? Now, if I look closely into this, and if I do a product of A, B, C, D, so that means that I'm going to do a product. So product is nothing but given by this particular sign. So the product of all the inputs. So I'm going to write it as product of GI HI, which is nothing but A multiplied by B multiplied by C multiplied by D. So if I do that, I'm going to have a product which is free of the variables x, y, z. And the reason is very simple. If I look into each of these variables, and if I multiply this, it will get cancelled. So the x variable will get cancelled with that of, here, the b variable. So if I multiply a and b, I'll get the x variable will be cancelled out. If I multiply a, b, b and c, I know that the y variable will get cancelled. And if I multiply C and D, I know that the Z variable will get cancelled. So I will get a definite product value. A product value is what I will get. Right? So that's what I'm going to show you in the next slide. So what I've done is I've taken a product of this A, B, C, D. I've also written it in the form of GIHI. Remember that GIHI is the individual effort delays. So it's an individual effort delays. So let me write it down here. Individual effort delay, and the product of the individual stage effort delays, right, will be nothing but GIHI, multiplied for all the 4 stages, and I will get a value of 400 by 90. So if I do 5 by 3 multiplied by x by 10 multiplied by 4 by 3 z by y multiplied by 20 by z. So if I do a product of it, so it will be 5 into 20 into 20, which will be 400, divided by 10 into 3 into 3, which will be 90. So 40 by 9. So it's a definite value. Right? So that is something we have done. So we have got a product now of all this GIHI, and there is a new term, there's a new definition for this called the path effort. So if I do a product of all the individual stage effort delays, right? What is an effort delay? It is nothing but GIHI. That's an individual stage effort delays, right? So if I do a GIHI and then multiply with all the stages, I will get an definite value, and that we will call it as an F value, capital F value, which is nothing but the path effort, right? For that particular path from the input to output, how many number of stages is there? Right, that many number of stages. If I pick the effort delays, if I pick the effort delays and then multiply those effort delays, I will get the path effort. Right, so the path effort is nothing but the product of all stages effort delay. Right, and path effort will give me a definite value. So it will give me a value of, in this case, we have got a value of 40 by 9. Right, so what we have got is, we don't know the value of x, y, z, but the product of all those terms, we got it as 40 by 9. So if I have a plus b plus c plus d, right, this particular value I don't know, but if the product of a, b, c, d, if I can find out if it is 40 by 9 in this particular case, right, what should be that minimum A value, what should be that minimum B value, what should be that minimum C value, and what should be that minimum D value is the question. So that if I have the minimum value of A, B, C, D, right, I will get the summation of that to be a minimum value. Right, in fact, I should rephrase this. If I want to know what should be the minimum of the sum of A, B, C, D, sum of A, B, C, D, given the product of A, B, C, D, right? So that's what we need to calculate, right? What should be that minimum sum of this ABCD given the product of ABCD as 40 by 9? It turns out that if all A, B, and C and D all have the same values, if A is equal to B is equal to C is equal to D, then I will get the summation of this A, B, C and D to be the minimum value. All right. So in that case, if A is equal to B is equal to C is equal to D is 40 by 9, then if all of them has to be equal, then what I will do is A is equal to nothing but 40 by 9 and then 1/4 of it, to the root 1/4 root of 40 by 9. Right? So then I can easily say that A plus B plus C plus D is minimum. And you can take any kind of an example here. Let's say that, the product of A, B, C, D is actually 16. Right? So in that case, A value, so A, B, C, D, the product is nothing but 16. Right? In that case, my A should be nothing but 16 raised to 1 by 4. Turns out to be nothing but the value of 2. So the summation, if I use A is equal to B is equal to C is equal to D is equal to 2, then only I will get the sum of A plus, sum of A, B, C, D, nothing but 8, which is the minimum one. Right? I can always choose a value of A or B or C or D as nothing but different value than 2. Let's say that if I choose a value of 4 for A instead of, instead of a 2 value, if I choose a 4, and then, if I choose a B value of 2, and if I choose a C value of 2, and then D value as 1, my product will be 16. No, I know that won't change. But if I do a summation of that 4 plus 2 plus 2 plus 1, it will give me a value of 9, right? Which is larger than that value of 8. So what we are saying is, if the product value is known, and if I can actually take out the root of that, right, whatever, if there are 4 variables unknowns, then it will be having 1 by 4th root will be equal to that of the individual variables. The summation of those will be the minimum. Right, so in this particular case of 40 by 9, if I do a 1 by 4th root, I will be able to find out the individual G1H1, G2H2, G3H3, G4H4 allocated to 40 by 9 and then the 1 by 4th root of that. To generalize this, what I've stated here is to minimize the sum of n terms. So in this case, I have 4 terms because there are 4 stages. But if there are n stages, and if I want to minimize the sum of those n stages, where the product is known, then the individual term should be 1 by nth root of the product. Right? So this is kind of a very general statement applicable in the linear delay model for the n stages. So tomorrow I have a 6 number of stages. Then I'm going to find out the path effort, which is nothing but the multiplication of all the individual stages effort delay, and then do 1 by 6th root, right, for that particular f value, and then find out the individual effort delays values. All right, hope this is clear. So my individual fi value, f1, f2 and f3, I know that it will be nothing but 40 by 9 raised to 1 by 4, which will be nothing but 1.4519. All right. And if I actually calculate 1 by 4519 to individual G4H4 and then G3H3, G2H2 and G1H1, I should be able to find out the individual variables of X, Y and Z. Right? So it turns out to be nothing but 14.52, 12.65, 13.77, which will give us, right, the summation of, the GI-HI plus the 6 value, which is coming from the parasitic normalized parasitic delay, to be minimum. All right. What it also says is, right, so what we have done is we have taken the f value, which is nothing but the product, of the individual effort delays for the 4 stages. Right. So the overall delay, the overall minimum delay, right, is nothing but the summation of the parasitic for 4 stages, which turned out to be 6 here in this particular case, right, plus the number of stages and multiplied by, because each stage is now seeing 4 f raised to 1 by 4 as an effort delay. So what we had done earlier was if I make all the stages C the same effort delay, then we know that the summation of that will be minimum. Right now, if all the effort delays are same, then 4 multiplied by the effort delays will give me the overall value plus the parasitics of 6, which we have calculated earlier, should give me the overall delay. So that's what I have written here. So the delay, overall delay, minimum delay in this particular case for this particular stage, the single stage circuit, is the summation of pi, which is nothing but 6, plus n raised to n into f raised to 1 by n, where n is the number of stages and f raised to 1 by n. If I have n such stages, f raised to 1 by n will give me the individual stage effort delay, and then multiplied by n will give me the overall, the summation of all the n stages effort delay. All right. What it also says is, without even finding out the gate sizes, without even identifying what is x, what is y, what is z, that is the gate sizes, we can actually estimate the minimum delay. We can actually estimate the minimum delay based on the number of stages. Right, which is a very crucial component. We are not identifying what is x, y, and z, but before that, if individual stage sees the same effort delay, then I can easily find out what is the minimum delay. So I no need to calculate the x, y, and z values to find out what is the minimum delay of that particular path. Right? Hope you have realized that. Moving ahead. So if I have this x value calculated, if I have this y value calculated, if I have this z value calculated, for an inverter, we know that 2:1 inverter. So I need to make this 3 parts of this, where the 2 parts will go to the PMOS side, and then 1 part will go to the NMOS side. So that's what I've done. 9.18 will be the size of the PMOS, and then 4.59 will be the size of the NMOS. Similarly, for a 2-input NAND gate, we will make 4 parts. 2 parts will go to the PMOS, and then 2 parts will go to the NMOS. And for the 2-input NOR gate, we will make 5 parts. Out of that, 4 parts will go to the PMOS, and then 1 part will go to the NMOS. And lastly, this size of 10 is nothing but 2 parts will go to the PMOS, and then 1 part will go to the NMOS. So we'll make 3 parts, and 2 and 1 parts of it, which will be allocated to PMOS and NMOS respectively. So hope this sizing is clear now. So the sizing of X, Y, and Z, which is the gate sizing, and how it has been distributed appropriately to its respective transistors, right? NMOS and PMOS transistors. Hope this is clear. The last one, so what should be the minimum delay here? It is nothing but, so I'm going to call this as a minimum delay, and then underneath it, I'm going to write it as minimum, which will be nothing but the summation of pi plus n into individual stage, which is seeing f raised to 1 by n. So I have 4 stages here, so f raised to 1 by 4, which is nothing but 1.5419, which we have calculated earlier, turns out to be 11.806 is the minimum delay for that particular stages. With the load of 20C and then with the input inverter gate size as 10. So the overall delay, the absolute value of the delay, the minimum delay, of course, the absolute value will be multiplied by 3 into RC. And if RC is nothing but 1 picoseconds, I will get an overall delay of 35.4 picoseconds. Right? Hope this is clear to everyone. So in this particular lecture, what we had seen is we started with understanding the gate sizes and how it is kind of distributed to the individual transistors sizing, the widths of the transistors, especially on the PMOS side, on the NMOS sides for different gates. And then using that particular notation, we apply the linear delay model and then try to, for a one particular single path, whatever number of the stages is there, we were able to estimate the minimum x value, the optimum x value, the optimum y value, and optimum z value, so that the overall delay turns out to be minimum. Right? Remember that what we have identified is the optimum sizes of the gates. Once we identify the optimum sizes of the gates, we were able to distribute it and allocate the optimum width for the individual transistors.